My name is Hillary Hafner, and I've been working on air toxics projects at STI for almost a decade, and I get to listen to Mike today instead of me doing all the talking. So we look forward to this, and also Mike, we'll if we have some questions on our end, we'll try to type them in and help go through them.
That sounds great. Okay, so I'm showing it's 11:02. Well, I guess that's Mountain Time. So I guess we can go ahead and get started. We have a decent number of attendees available, so if there are any problems, or Hillary, feel free to jump in, and please ask as many questions as you have at this time. So we're going to start off today by talking about data collection and quality control. And on the bottom, as in previous presentations in the last 2 weeks, we talked about these various steps in the process. And the red box is collecting QC your data. This is after designing your full project, and part of the collection and QC data is addressed in designing your project as part of data quality objectives. And at this point, you're just trying to make sure that your data is of a known and acceptable quality and quantity for answering the questions that you're going to be doing in the data analysis and interpretation section. So we're going to be talking about ensuring high quality data, how do you prepare your data, and how do you validate your data. I'm sure this is something that's not as exciting to a lot of people as a lot of these other topic areas, but this is very, very, very important in terms of making sure that your data are acceptable for answering the questions that you are trying to answer. And a little bit of QC goes a long way in terms of improving a project. So we'll talk about that all today. So, all right. So one of the first things you can do is to provide up-to-date standard operating procedures and ensure that they are used consistently in terms of data collection and sampling process. And also, you should be scheduling regular meetings between monitoring staff and operators and the analysts and other people in the project to share ideas, identify problems, and resolve them, and to identify lessons that are learned as you go along in a project. And scheduling these meetings early and often will help to resolve early problems in a project that are going to come along, and having the analysts and the operators talking to each other, if they're not the same people, is very important in terms of making sure that any problems that are happening in the sampling and analysis part of the project are known by the data analyst, so that less time is spent trying to identify problems that are in the data that are well known by people who collected the data. So making sure that that conversation has already happened is very important in terms of saving time down the road. And then it's also very helpful to ensure that your data are reported with consistent units of measurement, naming conventions. A lot of these pollutants have a whole bunch of different ways to say them. Whatever way that you decide to use, whatever word you want to use. If you want to use, for example, one of my favorite air toxics is tetrachloroethene, which is also known as tetrachloroethylene, and also perchloroethylene. And all those names are acceptable, but choosing the same one will make all your database work and make sure that you're not misaligning data as you go along. So making sure that you choose one single name and sticking with it throughout the project is also an important step to make sure you've got the data that you expect to have. Okay. This slide has a pictographic that at first I didn't get, but I think I understand now. And the idea on this graphic is that the earlier you start doing data validation in a project, the less effort you have to spend doing that data validation, and the more data you will recover and have as usable at the end of the project. And if you wait until the end of the project to start doing your data validation, then if there were problems, that you will take more time to resolve them, and you'll be able to recover less data as a part of that. And an example would be if there's a problem in the sampling or in the QC of a single pollutant, for example, if you identify that after the first batch of samples comes back from the laboratory, then you have a chance to do some sort of remedial action to make sure that that data is of acceptable quality in later samples. If you wait until the end of the project to start doing your data validation, well, that problem can't be resolved at that point unless you do some additional monitoring. So if you do your data validation as early as possible. As soon as the data is available, you will save yourself a lot of time and effort later on in the project trying to fix data that is not meeting your data quality objectives. Additionally, if there's a problem at the beginning of a project that, for example, the operator knows about, by the time a full year of monitoring has gone on, they may have forgotten about exactly what's happened there, and they're going to have to go back in their logbooks, whereas if it's fresh in their mind, they'll not need to do as much searching to remember what that problem was. And so, again, doing things very early on in the process helps to maximize the amount of data that you're going to have that's usable and recoverable. And so that's sort of the point of that graphic. All right, this slide covers basically almost everything that we're going to be talking about in the entire first part of this webinar. So it's really full of information here, and it just sort of goes through a checklist of all the different possible data quality things that you might want to think about, and then data validation steps you might want to think about, and then some data treatment steps that you might need to think about when creating the project, and then when you're actually implementing and looking at your data for the first time. So under the first bullet, data quality 1, these are, and also data quality 2, both of those are things that you're going to be taking care of in your data quality objectives in terms of what analytical things you're going to do to ensure the data quality is good, and sampling things you're going to do to ensure the data quality is good. So method blanks, spike recoveries, method detection limits, uncertainties, and units are all things that are sort of done on the analytical laboratory side. And we'll talk a lot more about many of these later, but just in case anybody doesn't know what a method blank is, that's just analyzing a sample that doesn't have any of a specific type of pollutant in it and seeing what the analytical signal is for that, making sure that you're not getting noise that's interfering with that specific pollutant. Spike recovery is putting a pollutant inside a sample and putting it through your analytical process to see if you recover all of that spike, if you are within 10 or 20 or 30% of recovery for a known quantity of that pollutant within a sample. Method detection limits and a number of other performance characteristics are just a way of identifying what the analytical performance characteristics are for a specific pollutant, and we'll talk a lot more about that later. Uncertainties is just saying, if you have a sample, it has a concentration X, well, it has an uncertainty plus or minus Y that tells you how certain you are that a value is what it is, what the spread in the data might be given the analytical performance. And then units are just how the data is reported. Data quality 2, replicates, duplicates, and co-located data. We'll talk about this later on, but basically this is just a way of understanding the precision in your data, both your analytical and your sampling methodology. Data quantity is just ensuring that you've got enough samples to have the physical power to answer the question, and making sure that you're collecting all the data that you expect to be collecting. Data completeness is just saying, some samples aren't going to come back valid for whatever reason, so you just need to make sure that you have enough data completeness to be representative of the sampling period that you're interested in, and also that you have enough data above your performance characteristics of method detection limits to have a usable data set. And then there's a whole bunch of validation steps, which we'll be talking more about in detail later, but basically as you go up in level, this is just saying that you have more confidence that the data set is correct. The level 0 ones are just making sure that the laboratory data is consistent with what you expected it to be. Level 1 is internal consistency checks, which basically just means comparing the data set against itself to make sure that it is internally consistent. And in order to do these sorts of internal consistency checks, you have to have some sort of conceptual model of what the data should look like. And so having some idea of what the data looks like to do these internal consistency checks is important. Historical consistency checks is to compare the data against data from previous time periods and making sure that it's consistent with that. And spatial consistency checks is just comparing the data at one site to another site to see if they're consistent with what you expect their spatial differences to be. And then once you've gotten all that data validated and quality controlled, then you still have to do some treatment of the data to either aggregate it for summary statistics or treat the data below method detection limits if it's been substituted or censored, or if there's anything else that's going on there. Understanding what you're going to do with your data in order to finally prepare it so you can actually do your analysis. All of this is just the pre-analysis steps, although some of these things do start to get into the analysis phase. Okay, So I've been talking a long time about that.
Hey Mike, time for
yes.
a poll?
Sounds good.
Okay, we're going to launch a poll to see if you paid attention to that last slide. So basically the poll here is, which QC and validation methods are you least likely to use? And there's no wrong answer. We're just looking for, from this previous list, which ones you might have considered. Method blank spikes, MDLs, replicates, duplicates, collocated measurements, SOPs, audits, intercomparisons, or internal consistency checks. I've got only a couple people voting. All right, there we go. I'm seeing some action finally. Great, thanks for doing this. What we're trying to do with these poll questions, sometimes they're just kind of giving us information on what you're interested in. Sometimes they're quizzing you a little bit, and hopefully always informing you. So once I get up, let's see, give a few more seconds here. We'll keep it open for a full minute. And then we'll go ahead and close and post the results to you. At least it helps give us a little bit of a break, and also can give you a chance to see if you're hearing, kind of really hearing what we're saying. All right, I'm going to close it and share the results. And basically, looks like people are really interested in internal consistency checks, and then also SOPs, audits, intercomparisons, and then a little bit less on the others. So thanks. Great. Back to you, Mike.
Great. I think the least likely to use, though.
Is this, least likely? Sorry.
So I guess
I didn't even read
most
it right.
likely to use so it's inverted. The most likely to use the replicates and duplicates and collocated, and least likely to do the internal consistency check.
Did I read it right, or did I just say it wrong?
I think you read it right. I think
you
read it right.
All right.
Okay.
It's early still. Not enough coffee. Okay, back to you.
Right.
Sorry.
Did you hide the poll results?
Okay. Yes.
Okay. So first we're going to talk about method detection limits, and this is a big sticking point and has been for the last, well, as long as I've been working on Proxys, this has always been a problem. So I'm going to be talking about this we give this about 5 slides or 6 slides of discussion. So there's a specific definition of what method detection limit is, and the key thing about this definition is that it's trying to discriminate between samples that have no concentration of a pollutant and samples that do have concentration of a pollutant, and identifying when you're sure, at what concentration level you are sure that a value is not coming from instrument noise or sampling noise. And so we're trying to discriminate against false positives, having concentrations that are not really indicative of actual concentrations in the atmosphere showing up as and being treated as real results. So this cartoon figure basically shows if you have a true value of 0, there's no concentration of a pollutant in your sample, and you analyze it, you're going to get some distribution. If you analyze it 100 times, you're going to get some distribution of concentrations around 0, which are a function of the instrument noise. And for this particular example, the standard deviation around that true value of 0 is 1. So there's sort of a normal distribution around that true value of 1. And that method detection limit is a performance characteristic for that analytical technique that says at this concentration level, 3 parts per billion for this example, we are 99% confident that any concentrations measured above that level are coming from real samples with concentrations above 0. They don't have concentrations of 0 because they're basically, all of those concentrations are going to be below 3 parts per billion. So it's just a way of saying anything below 3 ppb, it may actually be coming from a sample that doesn't actually have any of that pollutant there because of the instrument noise. But anything above 3 parts per billion, we're 99% sure it's coming from something that actually has some sample about it. Now, that doesn't mean that the method detection limit is really saying that at that level we know exactly what the concentration of the pollutant is. What it's saying is that at that level we're sure that that sample, that individual sample, is probably not coming from, is probably real. It's probably not coming from instrument noise. Okay, so why is that important? Okay, so, okay, yes, all right. So here's a bar chart showing over time the number of, the percentage of samples in the air quality system, US EPA's data repository archive, which has millions of air toxics measurements reported per year, what fraction of them are reported below method detection limits? Well, you can see that it's been above 50% for the last 10 years, and it's not going down over time. So when these concentrations are below these method detection limits, we're saying, well, we can't really say with confidence that those pollutants are above or below a level of 0. And so we have less confidence in those samples than we do in samples that are above the method detection limit in terms of using that data to create annual averages or to answer questions. We're going to have a lot less confidence in pollutants that are routinely below these method detection limit values that we have. So we're really not measuring these pollutants as well as we could be in terms of having extreme confidence in the data. Now, method detection limit is one performance characteristic for an analytical technique. There's a whole bunch of others. It's an alphabet soup. This sort of goes through what some of them are. Limit detection is very similar to method detection limit in concept. It's basically a means of discriminating against a false positive. Limit of quantitation and practical quantitation limit both have the same sort of goal, which is to say at a concentration at that level, you have a very good certainty that the concentration can be measured relatively precisely at that level. So these levels are usually 3 to 10 times higher than method detection limits, and at that level, for the practical quantitation limit specifically, you are saying that you can measure that concentration with an analytical uncertainty of less than 10%. So you have relatively good confidence in that pollutant concentration at that level. Now, let it be known that with 50 or 60% of data below the method detection limit in the entire U.S. right now, there's very, very few samples that are measured that are above these quantitation limits. We really don't have many air toxic species that we're able to get to quantitation limits at routinely. Most of the time, we're measuring things where we have relative uncertainties of 25 or 50% or even 100%. So we know the concentration to plus or minus 2. So really, we don't have great certainty in any individual sample when we're doing air toxics measurements. And another performance characteristic that's specific to analytical laboratories is called the reporting limit, and that's often, that's a level at which a laboratory will not report concentrations below. And it's oftentimes higher than the method detection limit. And oftentimes, the concentrations are either flagged and said this is below the reporting limit, we don't trust these data. Sometimes they're censored, and they replace those data with some other concentration value, whether it be the method detection limit or the quantitation limit or with 0 or with some other substituted value. It's censored. And so if your analytical laboratory is going to be censoring your values, you want to try to get them to not do that, because for air toxics, so much of the data is below those reporting limits that you're really going to have problems later on in your data analysis if laboratory measurements are being routinely censored and substituted without your consent. Okay. So, an ongoing issue in the air toxic community is, we have so much data below method detection limits, and laboratories often report data which have been censored. We need to do something with those data that have been censored in order to make them useful, in order to create summary statistics, such as annual averages or median values or standard deviations, that sort of thing. So if you have censored data, you're going to skew your summary statistics in some way. And it's oftentimes better to try to treat that data so that you know what the impact of the data substitution method is on your data. And really, there's different philosophical choices on whether you replace the values with 0 or with method detection limit or with method detection limit over 2, or whether you have the capability to do advanced statistical techniques such as maximum likelihood estimation, Kaplan-Meier, or robust regression on order statistics. But basically, the key thing to know is if you are going to be doing some sort of data treatment, you need to know how it's going to bias your average concentrations. If you're replacing it with 0, the real atmospheric concentration is probably above 0, so you're going to be biasing your average concentrations low. And so the drawback of that technique is if you are replacing a whole bunch of values with 0, you're going to get false negatives where you're going to say, okay, well, my average is below my level of concern. Well, actually, it may not be. You just have a bunch of data points that are being substituted that are drawing your average down. In contrast, if you replace it with the method detection limit, you're going to bias your concentrations high, which is a conservative method in terms of you're going to assume that the real concentrations are higher than they actually are, and you're going to have a whole bunch of false positives, or at least you might have false positives. Then method detection limit over 2 has the benefit of being in between those two methods, but has the drawback of it can be either negative or positive in terms of its false result. And so you can have high or low bias, and you don't know which one it's going to be for any given sample. If you have a lot of data and you have the statistical capability, then the advanced statistics can be a better way of dealing with these sorts of things. But in practice, typically the improvement is going to be small, on the order of 10% at best, and it requires significant extra resources in order to apply those techniques relative to other methods. Okay. And I see that there have been questions. I'm assuming that, Hillary, you're going to be taking care of answering those?
Yes.
Okay.
The question was, actually it's pertinent to this slide. The question was, is there a link to the online workbook that we mentioned earlier, and the link is actually shown on this slide, but I also put it into my reply back as well. And right. I don't know if you out there can see the reply, even though I hit yes, shared all. But anyway, if you look under questions, you should be able to see the link, guys.
Right. And we should note that a large part of what we're talking about today, we did an entire webinar series on data analysis and data preparation last year, I think, and that is also online and has a lot more information than what we're going to be talking about today.
Right.
Okay. And the key thing to think about in terms of choosing what to do here is, if you have uncensored values where the lab reported anything and everything that was monitored by the instrument, you want to use the data as is. You don't want to have to substitute data unless you absolutely have to. However, if you have censored values where you know that the laboratory is either replacing things with 0 or with method detection limit or whatever they're doing, you may be able to, you have to make a choice on how you're going to treat the data. MDL over 2 substitution is sort of the middle road, easy technique. And it may be useful for aggregate statistics, and there's been some papers about this. And basically, your bias is going to be small, on the order of 10 to 40% for an annual mean, for a data set in which you have less than 70% of your data below the method detection limit. Now, there are lots of data sets and pollutants where more than 70% of the data is going to be below the method detection limit. And for those pollutants at those sites, you're really not going to have any, you're just going to have a high degree of uncertainty in those concentrations, regardless of what methodology you use and regardless of whether the data reported below the method detection limit or not. That's always going to be high relative uncertainty in those concentrations, and at that point, those are sort of the limits of our sensitivity in terms of our analytical and sampling techniques. And so, at some point, you really can't, you just need to have a more sensitive method in order to get that concentration. And there are going to be lots of pollutants where that's going to be the case in any monitoring study, unless you have specifically very high sensitivity analytical techniques that you will probably end up paying more for. And the statistical techniques that I talked about are described in the data analysis workbook, and they're also available for free in the R statistical package as add-ons. I can't remember exactly what they're called. But if you do use them, they aren't necessarily going to improve your data sets by a huge amount, especially for typical toxic data sets where you usually only have, say, 60 samples in a year. And for some of these techniques, they require more data. Or if you just have a large fraction of data below method detection limit, they're just not going to do that much in terms of improving your results. So here's an example of changing your this is an example of changing your study design early in order to address an issue that was identified. And so this is from the JTAP study, which is in Arizona, and basically it was determined that in 2004 the method detection limits were too high for the goals of the study. And so in 2005 they went with a different laboratory, and the plot here just shows the average detection limits in 2004 versus 2005. Anything above the dotted line indicates that the detection limits were lower in 2005 than in 2004. Anything below the line, the reverse is true. And so really butadiene and styrene were a little bit worse. Everything else was either the same or better. And so they did improve their their monitoring methodology in order to be more useful for their specific study, because the initial method detection limits weren't sensitive enough. And so they were able to get that changed because they started looking at the data relatively early on in the process. If they waited until the end of 2004, by the time 2005 rolled around, they wouldn't have had time to change the laboratories, because that takes, the lead time on that sort of thing can be months. So, okay.
Before you go on, time to launch a poll to see if everybody understood what we were talking about.
Sounds great.
Okay, I'm going to launch a poll. The poll question now is, which censored MDL substitution method creates the bias in average concentrations low, to bias those concentrations low? Is it MDL over 2, 0, MDL, using advanced statistics, or none of the above? Let's see if you were paying attention, everybody. We need Jeopardy music, Mike.
I can hum.
Oh, I don't want to do that. Also, earlier we had a question that I think I answered, and also that you answered on the next slide, which was basically, what happens if you use the raw data below the MDL? And actually, that's the EPA wants you to do that. So.
Right.
All right. Go ahead.
Yes, you do have. The key thing about the data below method detection limits, they may or may not be from a sample that has a value of 0, but on average, the uncertainty about those pollutants should be representative across. When you're doing a summary statistic, they should be okay. It's just when you're using a single sample that your uncertainty is going to be, you don't know whether that's actually a real value or not. But if you do a whole bunch of samples, then that uncertainty should average out and you should be okay. And so for annual means, that's the right method to use.
Okay, I'm going to close the poll. We have pretty good participation, and now I'm going to share it. And so, Mike, you want to talk about the results here?
I'll go ahead and let you talk about it.
Oh, you're going to let me talk about it. All right. Well, the MDL substitution method that would bias your average concentrations low is indeed 0. And so most of you got that right. And the other methods have a different, MDL over 2 is basically a mixed bias, could be high, could be low. And then the advanced statistics are trying to get a more precise, value for your averages. So anyway, that's what we have on that. I'm going to hide it and let Mike continue.
Okay. Okay. All right. So switching gears, we'll talk a little bit about the thing that people do the most in terms of sampling quality control. Replicates, duplicates, and co-located measurements. Replicates are typically referring to a single collected sample that you analyze multiple times using the analytical technique. So you can analyze it 10 times or 3 times or whatever you want. And that's a way of getting a precision in the analytical technique from a single sample. And just because I always think about bullseyes when I talk about precision and accuracy, if you think about a bullseye as a target, if you're shooting arrows at your bullseye and they're all clustered in the same spot, then that's good precision. And if they're all over the target, then that's bad precision. But neither of those are accuracy. You can be very precise but not be hitting the bullseye. You could be off to the right somewhere and you are biased relative to the true or the central true value, but they're a good way of, the precision is an important thing to understand about your data in order to understand the actual relative certainty in any given sample relative to some non-standard. Now, accuracy is that bullseye. Are you hitting the thing precisely in the middle? And you can have a bad precision but be centered around that bullseye, or you could have good precision and be centered on the bullseye. So obviously you want high accuracy and high precision, but co-located and replicates, duplicates, and co-located measurements are only getting an estimate of that precision. They're not doing anything about the accuracy of any given sample or any given pollutant. Going back to the actual differences between them, a duplicate sample is just a replicate sample that's run twice as opposed to run more than 2 times. Both of them, replicates and duplicates, are only getting precision for the chemical analysis. Co-located samples are when you take two samples that are measured at the same place, either using two sampling manifolds or splitting a line or whatever method you use to co-locate the data, and then you measure both of those things back at the lab and see how close they are. And that can give you an estimate of precision of both the sampling and the analytical technique. So both those errors are wrapped in there. If you have both replicates and co-located data, then you can get an estimate of the sampling versus the analytical precision and see where your possible problems are. And EPA's NETS program has the following co-located data standards. They want less than 25% bias between co-located samples, and we'll show some examples of that later. And they want to have less than a 15% coefficient of variation for each pollutant. And the coefficient of variation is when you divide the difference, the standard deviation of a sample by the average. That's the coefficient of variation. And correct me if I'm wrong there, Hillary. I think that's right.
No, I think you're right.
Okay, just making sure. All right. So if you have a whole bunch of, usually you can't really do that for two samples, but if you have a whole bunch of samples, you can get the coefficient of variation numbers. So this is some real co-located data that was taken in Arizona, and if you have good co-located data, then your slope is going to be close to 1 for your regression. Your intercept will be close to 0 because you shouldn't have any bias between the two samples, and your R squared, the statistics on the R squared should also be close to 1. And so slope will give you an estimate of your bias between the two samples. If there's, if the slope is much greater than 1 or much less than 1, typically, it's basically if it's 1, then it's a perfect correlation. If it's 1.3, then you're off by 30%, and if it's 0.7, you're off by 30%, et cetera. The R squared gives you an estimate of the precision of the individual measurements within that. So you can have a slope of 1, but have a poor precision because the data are scattered all over the place. In this particular example, the slope is relatively close to 1. It's within 0.5, and the R squared is a little bit below 0.9, which indicates that there's some imprecision in the individual samples. But really, that R squared is driven by those 3 outliers at the top. And so, overall, your confidence in your measurements is going to be somewhat reduced because of if you see something like this in your co-located samples. Okay. In contrast, if you look at this sample, which is from the NES-PERS study that's in Lewiston, this is looking at co-located samples at one of their sites. And you can see that the data are all over the place, what I would call a shotgun scatter plot. Really, there's no correlation. There's an intercept. The slope is 0.4, where it should be 1. And really, there's no correlation between these two samples that were collected right next to each other. So something is wrong with benzene in their measurement study. And so, is this a misidentified peak in terms of the gas chromatograph mass spectrometer? Is there some co-loading interference? Is there some growth in the samples? There's something going on with their benzene data. And they didn't look at it until too late in the study. And so really, there was nothing they could do at that point to improve the measurements. And so, looking at your co-located data, you don't want to see anything like this. And if you do see something like this, you're going to consider that pollutant to be of very poor quality.
And what's really weird about this is that benzene is pretty straightforward to measure. I mean, we know how to identify benzene in an analytical sample, so that was troubling, very troubling. I was going to launch the next poll because it's pertinent to the previous couple of slides. So
Sure.
Is that all right, Mike?
Go for it.
All righty. So co-located data provide an estimate of sampling accuracy, analysis precision, blank error, sampling and analysis precision, or analysis accuracy. So please vote. We'll see if you were following what we were talking about there.
And I should note, oh, sorry, go ahead.
Go ahead.
I should note that for this specific year, there was a number of different monitoring, I guess, programs that were having problems with benzene in the last couple of years. And so I don't know what was going on with benzene specifically, but there was definitely a problem that was not just isolated to this specific study. So, but another good reason to look at your data, if they had looked at this data, 10% of the way into the study, they would have seen immediately that there was a problem and wouldn't have lost an entire year's worth of monitoring data, perhaps if they had been able to mitigate or choose a different laboratory or do something.
Yeah, I wonder if that's coevolution or something. That's odd. All right, I'm going to go ahead and close the poll. We got good voting out there. Thank you. And now I'm going to share the results. And so it looks like most everybody selected sampling and analysis precision, which I believe is the correct answer. So that's good. And, you know, I think we talked about in the previous session or two the fact we're spending a lot of time on data quality, because obviously if your data aren't of good quality, they're not going to be very helpful to you in your project. And I think the number we had said earlier was 10 to 15% of your budget is going to go towards quality control and quality assurance. So it's a pretty big piece of what you're trying to do. All right, with that, I'm going to hide and let Mike continue.
All right. I think I'm going to continue. Okay. So the previous few slides have really been talking mostly about doing data quality control at the sampling and analytical levels. And now data validation is more talking about what you can do if you're the person who receives the data after all of the sampling and analysis has been done, after the program's been decided. This is what you can do with your data, even if none of those other steps have been done. So this goal is to look at the data set internally and externally to other data sets to see whether it makes sense compared to what you expect the values to be given the known monitoring conditions of the study. So, you know, we want to produce a database of values that are of known quality and quantity, and we want to be able to use them in the data analysis. So this is really the beginning of the data analysis section, but you need the analysts need to do some data validation in order to understand the data and you know, have confidence that the data is what it's supposed to be. And really, there's a whole bunch of things you can do, and we're going to be giving some examples of all of them. But the real key thing is to look at the data and what I would call play with it as much as you can and as much as you have time for, in order to understand what's going on and to identify things that are strange about it. And when you see things that are strange, you know, flag them, do something to identify that specific pollutant or sample or whatever, and look more into it to see if that's really what you think, if that's really going to be representative of what's going on in the ambient air, or if that's something that you can't explain and that doesn't seem to fit with what you should expect there. If it isn't fitting with what you expect and you can't explain it well, you may not be able to throw it away, but you can at least say, well, it doesn't make sense. I need to spend more time looking at this in the analysis phase and seeing how much it impacts our interpretation of the results. And I'm not going to go through talking about each of these individual types of things because we're going to talk about most of them later, except for sticking check, which is basically saying if you get the same value for a measurement over and over and over again, then that might mean that the data is being censored or reported in some way that is not indicative of the true variation in the atmosphere. And so if the data is stuck, you get the same value over and over, and that might indicate that, you know, you're dealing with censored data. Okay. So this is an example from the JTAP study, which shows 3 pollutants that are chlorinated hydrocarbons. There's dichloro-difluoromethane, CCl2F2, carbon tetrachloride, CCl4, and methyl chloride, CH3Cl. And each of those in the year that we were looking at them had known remote background concentrations. And by remote, I mean, you know, somewhere out in the Pacific Ocean or somewhere very uninfluenced by anthropogenic emissions of pollutants. These are pollutants that have long atmospheric lifetimes and they're well mixed in the atmosphere. And so we know that in the remote background atmosphere, they're going to have a concentration that is approximately this over the course of a year. And so if we compare the measurements at these sites, or at this one site, of these pollutants to those background concentrations and say, okay, well, if they're within 15-20%, that's fine, but if they're well below those levels, then there's probably something wrong with those individual samples. Well, then we see that June 8, 2003 and that August 7, 2003, some of these samples are well below their background concentration levels, and those might be indicative of either a sampling problem or an analytical problem with those individual samples, and we needed to do more work on that. So this is a good way of testing to see whether your data is meeting its expectations of what it should be. Now, most of the samples, however, you do note that are either at or above those lines, and that's good. That's indicating that the data is what you expect it to be. Okay. And it is possible to get a lot of these things from the NOAA network, and some of the other remote background monitoring networks do have estimates of these global background concentrations. And so these values are from 2003. They may not be representative of what's going on in the atmosphere right now. Okay, now I'm going to show a buddy check, which is basically just plotting a time series of two sites against each other that are nearby each other. And you can either do this as a time series or a scatter plot, but the key thing is to say, well, if they're near each other, you'd expect their concentrations to be relatively similar most of the time. And for these particular sites, for arsenic PM2.5, there's a known emission source near them. And so that they aren't always the same is not surprising, because if the wind is blowing from a certain direction one day that happens to be near that emission source, you might expect one of the sites to be higher than the other. But that's an indication that, hey, we're being impacted by that high emission source on that day, or we probably are being impacted. We might want to do a wind analysis on these specific days and try to point out, how much the annual average is being influenced by the impact of that large emission source at these two sites. Now, if there isn't a large emission source nearby, then you would expect the entire graph to be relatively similar most of the time. Okay, another data validation example, and this is one of Hillary's favorites. In the ambient atmosphere, in most locations, benzene and toluene are dominated by mobile source emissions, and so they have a relatively tight correlation. And so if you look at the top graphic, the lower sort of bound of the benzene-toluene relationship is sort of that typical benzene-toluene relationship where toluene concentrations are higher than benzene. The dashed line is the 1-to-1. Now that big red circle indicates hours or points where the benzene concentrations are well above the toluene concentrations for a specific measurement. And once you've identified that this sort of relationship is bifurcated or has some sort of odd relationship, you know that there's some other source that's impacting the benzene that's not impacting the toluene. And this particular site happens to be located near a coke oven emissions site, and when you do a wind direction analysis for these individual hourly samples, you see that the benzene concentrations are all essentially elevated when the wind is coming from a certain quadrant of the wind rows or wind direction. So you can really identify where the benzene concentrations are coming from, which happens to be that coke oven emission. So, okay. So those data may be suspect in the sense that they don't have the normal relationship, but they might also help to point out, oh, there's a specific individual source pointing at those sites. They're still valid. They're still real ambient concentrations. That is that emission source that's impacting the site. There's a longer list of things you can do when you're evaluating your data, but overall, you just want to be comparing your data to as many different things as possible to understand whether it's meeting your conceptual model of what the concentration should be at a given site for a given pollutant. So as we were just talking about, benzene is often correlated with other pollutants like toluene and ethylbenzene because of mobile source emissions. Well, they should go up and down together then. So if you have a particularly high concentration of benzene, if the other pollutants that are co-emitted with benzene and mobile sources are also high, then you can say, okay, well, that seems to be a valid sample. Just happens to have high concentrations that day. Whereas if none of the other pollutants are high, then maybe there's some indication that either that sample is wrong or that there's a new source that's impacting that particular sample. Having an idea of whether the concentration should be high or low during certain seasons or days of the week, that can also be helpful for identifying whether pollutants are meeting your conceptual model. Benzene we expect to be higher in the winter, and formaldehyde we expect to be high in the summer because of photochemical production. If you're not seeing that pattern, that doesn't mean the data is wrong, but it does mean you should do additional investigation to see what's going on with those things. If concentrations at different sites aren't meeting your conceptual model of where the concentration should be high and low on individual days or across the monitoring season, well then maybe you don't understand the emissions, so again, more investigation might be needed. A real problem is if you have multiple laboratories measuring data or reporting data to you, you might need to do audits or intercomparisons to see how well or how accurate the measurements at both sites are. If you can get co-located samples and have both labs measure them, that can really help to develop a relationship between concentrations of two sites, because it isn't always true that labs report the same values for the same data. And so understanding how labs might be biased is also important. And then, of course, there's, you might expect a site characteristic to impact things if you know that you're near an emission source, or specific unique events might affect your data as well, like 4th of July or other. If if you're near a baseball stadium and they do fireworks every time somebody hits a home run or something, those things might affect your analytical site, and so you need to know of those sorts of irregular activities that might impact your data. And when you do identify those outliers, just do as much things as you can with them to try to understand what's going on. Are they coming from a certain wind direction? Are they, do they have certain characteristics by day of week, or are they, or some other difference in emissions or meteorology that might be explained by looking at the two different high concentrations versus low concentrations? Look at the emissions activity nearby. Look at your local traffic patterns. Is there something going on that wouldn't follow those local traffic patterns, such as a baseball stadium or whatever that wouldn't have your typical rush hour time? And then, of course, go back and talk to the monitoring site operators and seeing if they, have any, oh, that sample was weird, oh, something happened, or somebody was smoking nearby. They may know what was going on with that data and be able to tell you if you see something. Talking to the people who collected the data is always a good idea.
So Mike,
and sort of that.
So hey, Mike, this sounds an awful lot like data analysis to me.
Yes. And as we try to talk about, data validation is the first step in data analysis and getting to know your data. So
yeah.
We've kind of already talked about the lessons learned, but look at your data early and often. Always validate your data, because if you put something like that benzene data into your data set and try to draw conclusions from it, then that may not be a reliable. You may come up with the wrong decision because the data is not meeting your quality objectives. And if your analysts and your operators aren't the same people in terms of your collection and your data analysis, have them talk to each other, because it's usually the operators often have unique knowledge about what's going on individual samples. And from the NATS program, there's inter-laboratory analyses being done to sort of test how well labs are doing at measuring data, and there have been specific pollutants that aren't measured particularly well. So that could be influencing data comparability if you have multiple laboratories within an individual study, or if you have different laboratories over time. Both of those can influence what your concentrations are year to year or site to site. So, but as a result of the intercomparability test, there is better comparability over time as the performance evaluations are continuing. And with that, I am going to open up the next
on to data analysis.
Data analysis section. Okay. Have there been any questions or anything in the meantime? Is there a good? This is a good time to sort of talk about what's going on.
No, I haven't seen anything recently. I'm kind of curious why. I mean, we've seen data below detection for a long time, and it seems like it's gotten worse. Is it because concentrations have been coming down, so that there's more data below the detection limits?
I think that's part of the issue. I think also that we're monitoring in cleaner areas. We used to just monitor in the sort of, I don't know, the dirtiest, but the biggest cities, which would be expected to have the highest concentrations, and now we're monitoring in more background sites and more rural sites, and all those places have lower concentrations, and so we would expect higher rates of data below detection if we haven't made our methods more sensitive over time as well. And although some of them are more sensitive, they may not be sensitive enough to meet, we know that some of the pollutants are going down by 5% a year or so. So, that's the case. You've got to improve your method detection limits by 5% per year, and I don't think that's really been happening on average. So.
Yeah, we haven't really seen that, have we? Interesting. Thanks, Mike.
All right. So we'll be talking about each of these areas that are listed here in bullets. Although, if I remember correctly, most people are not interested in methods evaluation, so I'll go through that most quickly. And then once we finally get a trend characterization, you get to listen more to Hillary, and I get to stop talking. So you get about another 40 minutes with me. So, all right. So the key thing that we want to be showing, or at least that I would want to show with data, are that the data are of sufficient quantity and quality to meet the project objectives with statistical certainty. If you can put an error bar on something and show that it is different than something else, then people are a heck of a lot more likely to believe you than if you just have 2 points and there's no errors associated with that or uncertainty associated with that. And so, being able to put those error bars in there and correctly address them is a function of knowing the uncertainty, both your sampling and analytical, and your temporal representativeness of your sampling study, having enough samples where your uncertainty goes down as a function of the number of samples raised to the 0.5 or square root, and then data quality. If you've got biases or precision issues, all of those things are going to affect what your ability to say something about the data. And so if you're able to put those error bars on something and use your evidence-based comparison to your initial hypotheses that said, okay, this is what we're going to test, this is how we're going to test it, you plot the data up, then you're able to accept or reject your results and say, yes, that shows that this is indeed the case, or no, that's not the case, in terms of what you were trying to prove at the very beginning of your study. So this is really where, after you've done all the groundwork, this is where you're really trying to prove or disprove what was going on in your area, whether there's spatial gradient or whether emission sources are causing a certain problem or not, or whether something else is causing the problem. So this is really where you're trying to prove what's going on. And we've already talked about all these, and I'll just be going through each of these individual topic areas to discuss what types of analyses might be useful for showing how that happens. And for each of the different methods, we're going to be showing multiple ways of doing things, because you may not have the data in a certain way, but you might be able to do it another way, or you might be able to do it both ways and have even more confidence and weight of evidence that what you're saying is true. Okay. So let's start out with spatial comparisons. The NDOT study, the Nevada Department of Transportation near road monitoring study at US 95, some near road schools, and we measured black carbon concentrations on the left and the right plots. And what we're showing here is, in the left plot, we're showing as a function of wind speed, where the winds are the different colored lines, at the different schools when the winds are either upwind or downwind of US 95, what the average concentrations look like at each of these sites over the course of a year. And these are means with 95% confidence intervals. The units for the y-axis, which aren't shown, are micrograms per meter cubed. Basically what you see on the bottom plot is that when the winds are very high, 3 meters per second or greater, there's no difference in the upwind concentrations of black carbon. They're all about 0.25 micrograms per meter cubed. But as soon as you get to a downwind site at high wind speeds, you see a big increase in concentrations. And when the wind speeds get lower, the background concentrations of black carbon get higher and higher and higher, because basically there's less dispersion. And the gradient is still there. You still see this increased concentration, but the relative increase is smaller, although the absolute increase is about the same between upwind and downwind sites. So this is a good way of showing, there is a spatial difference and a directional difference when the winds are blowing from a certain way in terms of concentrations. And each of these individual schools, Fife Elementary, Adcock Elementary, Western High School, and Hancock Elementary School, are all at increasing distances from the roadway. So the Fife school is the closest, the Adcock is second closest, etc. On the right-hand side, we're showing box plots, which are basically just showing at one of those sites if the wind is upwind or downwind, where the gray is the upwind and the black is the downwind. You can see the difference between the median concentrations and the whole distribution of concentrations, where the boxes are the interquartile range. You can really see that the distribution, there is a statistically significant difference at each of the different wind speeds between upwind and downwind concentrations at this site, but that the relative difference is greater at the higher wind speeds, even though the absolute concentrations are much lower. So both of those show how you can look at concentrations spatially. And the box plot concentration here isn't necessarily useful for showing, this isn't actually a spatial comparison, but it could be used for a spatial comparison. Okay. You can also plot things on a map, which can be a very powerful way of looking at data. And basically, the larger the circle is on this map, the higher the concentration that was measured at a given site. The color coding indicates the fraction of the data that was below detection, and for this, we're just showing benzene concentrations. And you can see that some jurisdictions have more difficulty measuring benzene concentrations at certain levels of detection than others. And you can also just see, certain sites sort of pop out at you, but qualitative comparison. You really can't quantitatively compare individual sites using this sort of technique, but you can see where concentrations are higher or lower and where you'd want to do more analysis. And on the bottom right, we're showing cumulative distribution functions, which are one of my favorite ways of displaying data. Basically, this just shows for a given population of a county, going from 100 in a county to 10 million in a county, the blue line shows all the counties in the U.S. That's the distribution of county populations in the U.S. And so you can see, you know, at 0.5, the population is about 25,000 for the median county in the U.S. Whereas for the subset of counties with metals measurements, the gray boxes, you see that there's higher populations on average because we typically monitor in places where there are more people. And then for the VOC measurements, the red sort of the rust-colored triangles, you see that we measure in even more populated areas. So we have, you know, fewer measurements in lower populated areas. We don't have very many rural measurements. And then specifically for the Nez Perce County, I just showed on here where they fall in the distribution of VOC measurements and metals measurements. So you could see, hey, they tend to be a very low population county, and so we'd probably expect them to have lower concentrations on average than most counties in the entire U.S. And this came into play in this next plot where I'm showing the average concentrations for a year of monitoring from the Hatway site, which is one of the sites in the Nez Perce study, compared to the national distribution of concentrations in these bar plots for each of these different pollutants that were measured, both nationally and for the specific study. And you can see that for many pollutants, they're below that median and the 25th percentile, but for some others, like formaldehyde and acetaldehyde, they're above the 75th percentile, which, given their low population relative to other places that are monitored, is kind of surprising. And so there's probably some source there that's causing high concentrations of some of the pollutants. And then another good way to do a spatial comparison is to look at a pollution rose, and I'm pretty sure that most people have seen a pollution rose, but basically this just plots what the concentrations are and how frequently the concentrations are coming, or how high what the distribution of concentration is when the winds are blowing from a certain direction. And so the size of the bar indicates the frequency with which the wind blows from that specific quadrant or direction, and then the colors indicate the typical concentrations when the winds are coming from that quadrant. So you can see that the winds are typically coming from the south and the southeast in the specific area, and that sometimes you get the highest frequency of high concentrations when the winds are coming from those directions. Okay. All right, so all of those examples are ways of doing spatial comparisons. You know, if you can put multiple analyses together that show that, you can, you know, prove that, you know, your concentrations are statistically significantly higher than other sites. So you can show a spatial gradient. You can show that the concentrations are higher when the wind is from a certain direction, which might indicate a nearby source, or which might indicate a specific meteorological pattern that's occurring. You can show that your concentrations are higher than other sites in the community, the state, or the nation, which can be a very useful thing for showing that your concentrations are in fact impacted by a specific emission source or a meteorological phenomenon, or you're higher than expected given the local population and emission sources. All of these things are ways of doing spatial comparisons. Okay, and conversely, you can also show that these things are lower. If you have a low concentration site, you want to show that you're lower than everyone else in the country and how clean your air is. That can also be a goal of a spatial comparison. Okay. Moving on to emission source characterization. Okay. The first and one method that I almost always think of first when I'm thinking about emission source characterization is chemical source profiles, looking at the specific fingerprints of chemicals that come off of a specific emission source. So if you know that aluminum and iron and manganese and titanium are all from soil, and you see that they're all high in specific days, then you know that you're likely to have a soil sample. You can identify your chemical source because these things co-vary together very well. And then it can also be used to identify sources that don't seem to be, that you don't know what they're coming from. So for example, in this left-hand plot, I'm showing this chromium-vanadium factor. Well, we didn't know what was emitting the chromium and vanadium, but we know that it is being isolated as a factor in this particular thing because it was showing high fractions of chromium vanadium coming out of that specific, on those specific days. Similarly, the pollution rows can again be used to point towards specific emission sources. The concentrations are high when the winds are blowing from a certain direction, and that can indicate that that source is impacting that site. Additionally, you could do trajectory analyses. This is another way of using a wind rose where you basically plot your emission sources on a map, and then you show where your monitoring site is, and you show that when the winds are blowing from a certain direction, that you get high concentrations from that, that you get higher concentrations than average from that specific day. And this is an example from Detroit showing that you know, a specific industrial area with manganese emissions is in fact impacting a site downwind. Another way to characterize an emission source is to look at the temporal variability in the pollutant concentrations. A diurnal profile can be used to identify emissions activity. In the plot on the left, there's 4 different typical diurnal profile patterns are shown here. On the top is a midday peak, which shows concentrations that are highest in the middle of the day. Ozone shows this type of peak. So do formaldehyde and acetaldehyde. Typically things that are secondarily produced or are emitted more during the day might have high midday peak concentrations. The second profile is a nighttime peak, where basically you get the highest concentrations at night. This type of emission activity may have no change during the day. It may just be something that's emitted at the same rate at all times. And the decrease in concentrations during the day is caused by increased mixing heights. The morning peak shows a sort of what we're calling a rush hour peak. That's a good example of traffic emissions. We know that there's higher emissions of traffic-related pollutants at 7 and 8 a.m. for motor vehicles, and so pollutants that show this pattern are dominated by that sort of traffic emissions pattern. And then an invariant profile, one that shows no variability time of day, is one that is probably not emitted in your area and is probably background is coming from somewhere else and is not influenced by mixing heights or local emissions at all. And that's what you'd expect from an invariant pattern. A day-of-week profile, which is probably going to be more common for air toxics data than a diurnal profile, which typically we don't have as many sub-daily measurements. You can just plot your concentrations as a function of day of week, and if the concentrations are lower on certain days of the week, then that might indicate that there's lower activity of that specific thing. And so we're showing this for benzene. There's lower concentrations on, or statistically significantly lower concentrations on Sunday than other days of the week, which is which sort of matches our conceptual model that it's being emitted by mobile sources, and that traffic activity is lower on Sundays than it is on other days of the week. And so we've already shown this conceptual model of how you can sort of identify what your emissions activity profile looks like and then put it together with your other factors that influence concentrations such as solar radiation or stinks and dispersion in the atmosphere. And if you put those together in certain ways, then you can identify a pattern that will match your individual pollutants concentrations. Okay. Additionally, you could do a time series analysis just looking at concentrations over time. This is an example from the NESPER study looking at formaldehyde concentrations at the 5 monitoring sites that they had. And then the black line is sort of the running average across all 5 sites for the entire study domain. And what they really see, what we really saw here was that there's higher concentrations in the May to August time periods, where the high summer months, high solar radiation, high temperatures, and formaldehyde is probably being produced in the greatest abundance. And then there's very low concentrations in the winter. From, say, October through May, there's basically low concentrations, all below 1 ppb at all the sites. And so low variability, low concentration. So really this sort of high concentrations in the summers you know, indicated that the source was something that was emitting or being produced more in the summer than in other months. And for this particular study, if you remember from a couple of weeks ago, this was trying to identify emissions from a pulp and paper mill, and the pulp and paper mill emissions included formaldehyde. And if the pulp and paper mill, which operated year-round, was the major influence of formaldehyde concentrations locally, we would have expected there to be more concentrations in the winter when the mixing heights are lower and when the inversion layers are lower and when there's going to be all that formaldehyde from that pulp and paper mill are going to influence things more, but really we saw the opposite. The summer concentrations were the highest. And so we really think that some other source, like secondary production or maybe biogenic emissions, are really dominating the formaldehyde concentrations of this area. So this was a way of sort of comparing our initial conceptual model of what the pulp and paper mill emissions seasonal profile was versus what was actually seen in the atmosphere. All right, sort of the most advanced way of looking at emissions is to do receptor modeling, and we did some source apportionment work of VOC concentrations in Edmonton, Alberta, which is a really big petrochemical area due to the oil sands projects there. And the Edmonton East site is near a whole bunch of holding tanks and petrochemical facilities, and so it really had a whole bunch of industrial evaporative emissions of a number of different chemicals that were identified, whereas the Edmonton Central site was more located in their downtown area and had a higher concentration of gasoline combustion and diesel combustion sources in that area than the other site. And so this is a really nice way of showing that the two different sites had really different concentrations of VOCs in total and what the individual emissions were to both sites. And if you're very good, you can take the individual pollutants that are in your source apportionment study and apportion how each of the individual sources is attributed within your monitoring study. And so this was a apportionment of benzene at Los Angeles site. Most of it, almost half of it, is from motor vehicle, and then they had other different individual sources that were identified as contributing to benzene at that site. Okay. So we've just shown a number of different ways that you can point towards emission sources, such as chemical fingerprints, wind direction analysis, either by pollution roses or by trajectory analysis, looking at temporal activity to identify the emissions activity, looking at spatial gradients if you've got multiple sites, seeing how the concentrations vary between sites, and then you can also use receptor modeling, which is sort of the most advanced tool to identify and quantify your emission source characterization. And I think now would be a good time for a poll question, right, Hillary? Hello? Anyone?
Hey, I'm sorry, I had the microphone off. I'm not seeing the last slide. It's like,
You're not? Emission source characterization? Okay.
Yeah, it's not showing on. I'm seeing the first one with the pie chart and everything. Do you want me to launch the poll now?
Yeah, go ahead and launch the poll. It's just a summary of what we already talked about.
Got it. Okay, so the poll, we're going to do a flash poll here quickly. Which of the following methods is most reliable for source characterization? Chemical source profile, fingerprint analysis, pollution roses, trajectory analyses, temporal variability analysis or emission activity, spatial gradients, or receptor modeling? And we'll see what folks are voting. Good. We've got people awake out there. Yay. All right. We're going to give it another few seconds, and I'm going to close it. This also gives Mike a break, right, so you can get a drink of water.
Indeed. I hope you guys can't hear me gulping.
It's okay. All right. Another 5 seconds. I'm going to close the poll here. All right, here we go. I'm going to close it up and share it. And what we're seeing is people have sort of a mixture of feelings about these different types of source characterization methods. I think the idea here is that probably no one of them is the most reliable. I would say that you probably need to do a combination of these approaches. Depending on what kind of data you have available, what kind of source you're trying to characterize, one or more of these may be needed to do that. So with that, let's move ahead. Thanks, everybody.
Okay. All right. So we're going to move on to health effects assessments. And really, most data analysts aren't really necessarily health effects people, so this is simple analyses that can be done. We're not going to really talk about doing risk assessments, which is a different area of analysis and is usually needs to be done in consultation with a lot of other people, and is also can be very controversial. So having people that are risk communicators or health effects people on board for these sorts of things is very helpful. But as a data analyst, there are some simple things you can do to identify which pollutants are of concern, which ones are above levels of concern that don't really require any special training, and can help you to identify internally what the pollutants that seem to be of most concern from your monitoring study are before you hand the data off to the next group of people to do risk exposure modeling or risk assessment. And so this first slide that we're showing is just a very simple flow diagram for identifying whether a pollutant concentration is reliably above or below a level of concern. And so the first step is to say what fraction of your data for that specific site and pollutant is below your method detection limit or your other performance characteristic that you find to be important. And I chose 85% here. You can make that more stringent if you want to have a higher criterion there. If the answer is yes, then you can say, okay, well, my data is mostly below method detection limit, but is my health benchmark above my method detection limit? Well, if the answer is yes, then I know that my concentrations are below my method detection limit and my health benchmark is above my method detection limit, so my pollutant concentration is below the health benchmark. So it's the first gray box. We know that the upper limit of risk is, are below our level of concern. Now, if the answer is no, so that is health benchmark above method detection limit, well then I've got data below the MDL and I've got a health benchmark below the MDL. Well, I can't really say whether the site pollutant is above or below that level of MDL because the data is not good enough. Okay. Now, if you're lucky enough to be on the second side where the first answer was no, you can just directly compare the site average concentration to the health benchmark, and you can get that blue box where you can say the risk is above your level of concern, and you can sort of have some estimate of what that level of concern is. Or you can say no, where the pollutant concentration is below my health benchmark, and you can say by how much. And so on the right-hand side, you can sort of characterize what the actual levels are. On the left-hand side, you may not be able to characterize what the levels are, but you can say whether they are above or below the level of concern some of the time. Okay. All right. Another thing you can do is to compare your model data. You can compare monitoring data to model data to see how well your monitoring data is comparing to the model data from some modeling exercise. And this is an example from the NADA 2002 results, I believe. And it shows box chart showing the interquartile range, so the 25th to 75th percentile of monitors nationally for each pollutant, and the median concentration, that light gray box. It shows the two line that shows the factor of 2 line essentially just shows that the model to monitor ratio is within a factor of 2. And any pollutant where the box is mostly within that factor of 2 range you consider relatively well modeled, and you might be able to use that. You're going to be more, that data is going to be more reliable for using modeling data to assess risk. Whereas if there's pollutants that are well below that line or well above that line, you may not have as much confidence that those pollutants are being modeled well, and therefore may not want to use those sorts of data, the model data from that result, to assess risk because the concentrations don't seem to match what's going on in the ambient atmosphere. Of course, it could be possible that the ambient monitoring data is incorrect too, but that, that might need to be checked into as well. In addition to just looking at whether a concentration is above or below a level of concern, you can look at how far above or below a level of concern is and try to prioritize which pollutants are most important for your local area and which ones are not important for your local area. And this is a plot that is from a paper that we put out in 2009, I believe, in Environmental Health Perspectives. And it shows the 10th to 90th percentile concentration ranges divided by their health benchmarks of concern that were listed by the US EPA, OAQPS. And the black boxes sort of show the ranges for pollutants that are that are in particle form. There's PM 2.5, there's PM 10, and there's TSP. All three of those are overlaid on each other with the different black, green, and purple bars. And the key thing with this is that we basically just characterize which pollutants were typically well above the level of concern or above the level of concern at more than half the sites nationally. And those are the pollutants in the A box. There's also pollutants in the C box, which are typically below the level of concern at most sites nationally, either with directly measured concentrations in the top C box or with method detection limit substituted concentrations in the bottom box. So those are pollutants where more than 85% of the data is below the method detection limit, but the health benchmark was above that level, and so we were able to say with some confidence that those pollutants are actually below the level of concern nationally. On the right-hand side, we show the number of sites that were used to make that national distribution, so you can really say how many pollutants are of concern. Okay, and then there is that B box, which we sort of talked about earlier. These are pollutants where more than 85% of the data were below the level of concern, so these are essentially substituted annual averages that really may reflect the method detection limit more than the actual ambient concentrations. Dividing those by the health benchmarks, they're still above the level of concern, and so we can't really say whether these pollutants are actually above the level of concern or not. We don't know because we're not able to monitor them sensitively enough to prove they are above or below the level of concern nationally. Another thing you can do, and this is from the NES-PER study, is just to compare which pollutants are most important for your local area by dividing your annual average concentrations at all your sites or at your maximum site by your level of concern. And so this was for the NES-PER study. They basically found out that formaldehyde was much, much more important than any of the other pollutants, or in fact all the other pollutants combined. And as I'll mention again, this study was trying to identify emissions from the pulp and paper mill. And really the key pollutants that are emitted from a pulp and paper mill are chloroform and tetrachloroethene, which are way down at the bottom of the risk list. These really are contributing a small amount of the local risk compared to a lot of the other pollutants. And so in terms of the impact of that pulp and paper mill in the community, we weren't really able to see that they were responsible for a large fraction of the air toxics risk for the cancer risk. And it should also be noted that for this particular study, health benchmarks can be 70-year exposures. This particular set was 30-year exposures, so some of the numbers may not match up with what you're used to in terms of seeing the level of risk. And that's just a choice that they made in terms of what health benchmarks to use. But in this case, it's really which ones are most important was sort of the key principle. Okay. And so summarizing the health effect assessment, we can really use ambient data to perform simple risk screening just to say whether it's above or below level concern. You can estimate the risk-weighted concentration levels to estimate risk levels at an ambient station. You can validate and evaluate modeling efforts which are used to evaluate risk, and you can identify temporal variability in concentrations for use in exposure models. For some pollutants, like formaldehyde that are highest in the summer, people may be exposed to more of that because they're outside more than a pollutant like benzene, which is typically higher in the winter where people are typically inside. And so the temporal variability can also be an important component of exposure, which we really didn't talk about here, but that can be a useful thing to contribute to a monitoring study, or a modeling study. And I think it's time for another poll.
Yes, we have a poll. Sorry, I keep forgetting I have my microphone turned off. All right, we're going to launch a poll. And the poll now is, which of the following statements is false? Health benchmarks can be very uncertain. Ambient data should not be used to evaluate models. Health benchmarks are based on linear extrapolations. Or risk assessments help prioritize pollutants of concern. So let's see what you're thinking out there. So we'll give it a few more seconds here. Great. Keep voting.
So I haven't been seeing many questions. Have there been many questions that have been asked?
We just had a question on, is upper bound inhalation risk the same with upper limit of risk? If they are the same, what's the difference of upper bound with just risk? And I basically kind of said we weren't really talking about upper limit of risk is really what risk assessment folks think about, whereas we're really just comparing concentrations to a screening level. So I'm not sure I answered the question very well. But really, we're just using those as comparisons to numbers. We're not looking at like whether or not all the pollutants we're looking at have the same part of the body that they affect, and all the things that a risk assessment specialist would look into.
Yeah, and I guess I would say that that might refer to the. I know that the risk assessment guidelines are to take the 95th percent upper confidence level of the annual average. So
right.
as opposed to taking the annual average, you take the annual average, you take your uncertainty, and you take that upper bound. And so that would be a more conservative method of comparing to these risk concentrations. And so you make sure to include all of those methods. So I think that might be what they're talking about there. And so it's not necessarily the upper, what we're talking about is not necessarily the upper limit of risk. You can try to characterize what the upper limit of risk is using those other techniques, because there is uncertainty in our annual averages that we're not accounting for when we're doing a point annual average comparison.
So yeah, I think that I think you're right, and not very much of the data is above those, like the PQLs and et cetera that we've talked about that that the risk assessment folks want to see. We just don't have concentrations that high usually. So I think this was a tricky question because which of the following statements is false? I was going to vote on the second one, which is ambient data should not be used to evaluate models, because I think they are useful for evaluating models. Did I get that right? That's what I was
intending the right answer to be, but that doesn't.
And
it is a tricky question. I didn't talk about the third thing, which was the most guessed about thing in the entire thing, which is probably why it was guessed about most. Most health benchmarks, at least as far as I know, are based on linear extrapolation because they have. I think the level of absolute certainty is the 1 level where if you get exposed to this concentration, then you are going to get cancer. And then they extrapolate backwards linearly using some usually using a linear method to say, okay, well, if this is your 1 in 1 chance of getting risk, and we divide it by essentially 1 million to see what the 1 in a million chance of getting that cancer are. So just a simple linear extrapolation. I think that's true, although I could be wrong. So if there are any health people out there that know the right answer to that and want to argue with me, then please do. I will accept being wrong on that one.
Great. I think on methods of evaluation, we should probably not spend a lot of time, because if I remember from a poll earlier that people weren't as interested in this.
Yeah, so I'm just going to zip through this.
Great.
The key point about methods of evaluation is a number of ways to do it. Most people aren't as interested in this for the community scale modeling studies they are doing, but it can be interesting to think about. This is the first slide is just showing the potential growth of acrolein within canisters. So they started out with a known concentration and they measured it every few days. And for a few of the canisters, the concentrations increased over time, which is indicating that if you don't get your canister directly to the laboratory, then you might have some acrolein that's showing up within the canister that wasn't there on the first day when you analyzed it, which can be a bad thing when you're trying to quantify what's going on in the atmosphere as opposed to what's going on in your canister. Another way to evaluate a method is just to compare concentrations using a time series, look and see if they have the same shape, the same relative response, and you don't necessarily have to have the same concentration because, for this example, black carbon and sunset elemental carbon, they're not measuring the exact same thing. One's an optical, both of them, well, one's an optical method and one's a thermal method, and that one's burning off all the elemental carbon and one is just sort of seeing how dark it is. And so you wouldn't necessarily expect the same response, but if they respond in a similar way over time, that does indicate that you're probably measuring similar things. So that can be a good way to identify a relationship between the two of them. And then this is an example of those same two pollutants, the aethalometer black carbon and the sunset elemental carbon, put on a scatter plot against each other. And then the nice thing about this plot is that they're also showing organic matter concentrations in micrograms per meter cubed, which is a different pollutant, and seeing if there's a change in the concentration relationship as the OM goes higher. And really, it seems like the concentration is pretty linear regardless of what the OM concentration is, which was a surprising result for this particular methods evaluation. And so really you want to evaluate against standards as possible and against other pollutants and, against other existing methods to identify any biases you might have and see how things change under real world ambient conditions. And a new method is oftentimes the best way of understanding what's going on in the atmosphere, because if you aren't measuring it if you aren't measuring effluents, then you don't necessarily know what's going on with it, and so it can help us to understand what's going on with our local emission sources or the local chemistry of the pollutants. Okay. And now I think it is Hillary's turn, and so I'm going to try to.
So you need to give me, if you can, control, I think.
Your mouse input always has priority. Okay. So I think you have control, Hillary.
Do I? I don't see it. Can you give keyboard mouse to me?
I already did.
You did. That's weird.
So you might have to go down to the bottom left to try to move the slides.
Okay, let me try that. Hold on. Let me show a different. Oh, that doesn't do it. Bottom left.
Where the arrows show up. That's how I had to move it when
I did. I hit it, right? Trend analysis. Did you change that or did I?
I am not touching anything right now.
Okay, let me try it again. Sorry, hang in there. Actually, what else we can do is we can launch a poll while we're going.
Okay.
You know what? I don't. Go ahead, Mike.
You have the keyboard and mouse.
It's
Click on the. Take your cursor and click on the just that slide there, and then try and use the page up and page down.
Yeah, I'm not.
Are you getting it now?
No, and I'm still seeing Mike's mouse.
Should I make another attendee the presenter, Mike?
Wait a
Well,
minute.
you know what we can do is I'm fine. I'll just.
I just made Hillary. Give me 1 second. You should be the presenter now.
Oh, okay. Show my screen. There we go. So I just need to get the. Okay, so I just have to take us to where we are. That'll work.
Okay.
Let's see. I'll get us to the right place.
And did you want to do a poll now, you said?
Yeah.
Sure, I'll go ahead and launch the poll, Hillary.
Let's launch the poll. Okay, sorry. Okay, now I'm good, right? Everybody can see my screen, I hope. And we're going to launch a poll that has no wrong answer now. We're going to basically be asking you, are you going to see? You got it open, Mike?
Yes. So it's saying, what do you find most difficult about trend analysis? Understanding the reason for a trend or no trend, handling data below detection, addressing effects of sample analytical method discontinuities, or properly quantifying the trend. And we're reaching the end here. We've only got about 10 slides left, so thank you everybody for your patience in listening to me for the last hour and a half.
I've had a couple people have asked if we were there's a clicky noise or if we were hitting something near the microphone. We don't seem to be doing it here, so I don't know what's going on. Oh.
Okay, so I just closed the poll, and
Great.
Looks like handling data below detection and addressing effects of sampling analytical method discontinuities are the two biggest issues that people are seeing.
Great. Okay. No, that's really helpful. All right. So I guess Mike, you're going to try to mute here while I start talking, and hopefully that'll correct whatever the problem is that we're hearing. Just put another question up if you're having problems, and we'll try to handle it. All right. Thanks, Mike, very much. So we're going to spend the last bit here talking about a little bit more data analysis methods and interpretation. And I think one of the questions we ask a lot of our data is whether we're seeing pollutant concentrations coming down over time as we put in new rules, or and the goal is really to decrease the amount of these pollutants so that we're not being exposed to them as much. So one of the things that we've done working with EPA has been developed trends analyses and trying to show these air toxics trends, and they're very tricky, as we've been talking about, in really dealing with handling data below detection. Have there been method changes over time, or sampling and analytical method changes over time? How do you quantify these trends? How do we understand whether or not the trend makes sense? And so we've been spending, Mike and I have been spending a lot of time thinking about these questions. And so this graphic, actually, I really like it, because essentially, if we looked at we looked at air toxics across the country over a period of, let's say maybe this is 2003 through 2008. I can't remember exactly the time range here, but it's over several years. And we tried to look at the central tendencies of the data across the nation. And this line down the center here is there's no change per year. Anything to the right is showing an increase over time, and values to the left are showing a decrease. And these ranges are essentially just across the 10th to the 90th percentile sites across the country. And what we're seeing pretty consistently across the hydrocarbons is a decline over time of about 5%, and pretty much any pollutant, any time frame that we looked at for these pollutants, even going back with some data sets from 1990 forward, we're seeing about this percentage decline over time. So it's pretty interesting, and we really seems to be attributable to reductions in emissions from vehicles and fleet turnover as we're getting cleaner cars on the road, and that's been sort of backed up by some emissions studies in some tunnels. So it's pretty exciting. But in general, we're seeing declines over time. Okay, sorry. There we go. So one of the things that came out of our trends analysis, however, was you can't just look at your ambient data. You need to also look at the detection limit information that's available. As we were looking at some data, we came across, this is a graphic showing manganese in particulate matter, PM2.5, the concentrations over the years, and we happened to plot the average concentration and the average detection limit, and lo and behold, those two plots looked awfully similar. And I would not expect the ambient concentrations to show the same trend as the detection limits, because if they are, then that's signaling that there's something not quite right. So what we looked at here was we called up the folks that we know these data really well, and we found out that they had indeed actually published a paper that talked about that their real detection limits for this data set were actually the real detection limits were actually higher than what they were reporting at the time. So essentially, that these concentrations shown here were actually probably data below detection. But this was essentially something that we found by just actually looking at some of the graphics and thinking these just don't make sense. So really questioning the data is very important. And looking at the data in many different ways is really helpful here. So here's how a trend in pollutant concentration should actually look. And this is a case where we have concentration of benzene over this 1997 to 2000 trend. And it is kind of a funky graphic, I apologize. But essentially, we plotted the mean concentration and standard deviations for each year. And you can see this nice decline over time. And the detection limits really aren't looking at all like the trend that we're seeing in the ambient data. So we have more confidence that this trend that we're seeing here is actually makes sense, and is that it's not showing an influence from any change in detection limit, which there certainly has been over time. So we feel comfortable that this is a real trend. So quantifying trends, there's many different ways to do this, and I don't know that the jury's sort of out on the best way to do it, and it kind of depends on your data set. But you can certainly initially look at the first and last year of a trend period, or look at two multi-year averages to try to understand what the percent change might be. We use a lot of just simple linear regression and to help us assess the magnitude of the trend over the trend period. And then you can also use, when you do the linear regression, you can also do things like an F-test, which we've listed at the bottom here, to test for significance of whether or not the slope of the trend line is statistically significantly different than 0. And so that gives us some measure statistically of whether or not the trend makes sense. So there's other quantification methods. Percent difference between the first and last year gives you some rough sense of the change, but you need to look at your data before you use those numbers, because there can also, you might just have hit a low year at the beginning and the end. You can also look at the difference between two multi-year averages, and I'm going to show you an example of a trend where you really needed to do that, because there was really, if you looked at the data, there's just two different data sets that you need to handle separately. That also helps you take out meteorology if that's, you can kind of do like this rolling average, 3-year rolling average or something. And then we like to use this percent change per year. that's provided by the slope of the regression line, and that also sort of helps you. You can then compare across data sets that have been collected over differing time periods. So as I said, we could go back with some pollutants like benzene back to 1990, and if you have this percent change per year, you can compare those data sets to other data sets. So it's a pretty slick way to look at the data. All right, so we talk a lot about how you really need to look at your data, no matter what whenever you're playing around with data, make sure you're graphing it in many different ways. And here's a case where we have benzene annual averages from the early 90s into 2000, and you can see this very big step change in concentration between 95 and 96. This happens to be California data. And between those two time periods, something called reformulated gasoline came in, where benzene percentage in the fuel went from something like 30% down to a few percent. So there was a significant difference in the benzene concentration, or the amount of benzene in gasoline, and we would anticipate that would also be a significant change in the ambient data. And indeed, you did see this big drop in concentrations of benzene. So this is a case where I would argue that while this line does, a linear regression across all the data makes some sense, I really understand a lot more about it if I look at the difference between these two time periods of the data. I think I learned more about the concentrations in that case. Again, there's different ways to visualize data. We've shown you some box plots. The thing that's nice about a box plot is that it's showing you all of the data in a concise way. So it's showing you the highest points, the lowest points, the interquartile range, the 25th to 75th percentile. The median is here, and there's a confidence interval around that median based on the number of samples. Lots of samples, you have a smaller confidence interval. You're more confident that that's the central tendency of the data. If you don't have very many samples, then that notch gets bigger. So it really helps you compare from year to year. When those notches don't overlap, that means there's a significant difference. When they do overlap, it's harder to tell the difference. And this is a case where there's something really weird going on in 2002 in this data set, and it doesn't look like any of the other years. So, does that signal that there was some sort of methodology change? Was there something really weird going on with the meteorology? I mean, that's something I would actually, by looking at this data set, go back and try to understand what was happening. This is the same data set, just showing it with a different way to show the data, just showing like the 95th percentile, the annual averages, the medians, and the 5th percentile. But I tend to like these. They're the box plots, but they're just a little bit more they're harder to explain to some audiences. So it may be a case where you need to have something a little simpler to show. So one of the things that we try to do, obviously, is we're going to try to compare trends across sites, and this is just illustrating two different sites where we were looking at benzene trends. And this is a case where there is a statistically significant downward trend in benzene at this location, and we have a lot of confidence in that trend. And the detection limits are low, doesn't seem to be affecting anywhere near the concentrations that are being measured. But in contrast, this is a site where there seems to be very little trend, even though we're pretty confident that it's an insignificant trend. That we're in other words, there's not much of a trend, but we're confident in the data because the data concentrations are well above detection, and there just doesn't seem to be much happening as far as concentrations going down in this location. There doesn't seem to be any big outliers that are affecting the trends, et cetera. So we know a lot about both of these data sets, and showing that in those two locations, there's really something different occurring with benzene. And if I remember right, these are not from the same city or anything. But there's just a different effect going on in those areas. All right, keep moving. So back to one of our examples from these different projects that we've been talking about throughout our conversations with you. This is the Michigan DEQ percent change per year for the pollutants that they were interested in or they were monitoring for. And again, looking back at the national trend line, we have the 0 here, and again, the sites that had increases over the year would be on this side, and the decreases would be on this side. And what we're trying to get across here is there's actually a dot for a data symbol for every site and every pollutant combination here, so that this was looking at them by site, okay? And so one of the things that I, was looking at this data is that for benzene, we're quite certain that there's a decline of 5 to 10% per year at these locations, and that's consistent with what we're seeing nationally. So that was interesting. And there's a certain increase for chloroform, which I'm not sure we ever really figured out, but it was a big increase. And other than that, most of these other pollutants were not statistically significant declines or increases. That there were either were too variable to assign, there was they weren't statistically significant, or it was only a probable increase or decrease. So this helped us at a glance, even though it's kind of complicated, start understanding what was occurring in the pollutants at the sites in the Michigan area. All right, going here. So this kind of harks back to a slide that we had earlier, which is essentially, are the data sufficient quantity and quality to meet our project objectives? And essentially, we're looking at uncertainty that's associated with sampling analysis and whether or not the data are in the right, we're collecting information in the right location, with the right duration, with the right frequency. And so that becomes, we need to try to illustrate that with our graphics, and that's what we've been trying to show you throughout here. And then we're also questioning whether or not we had enough samples to answer the questions that we were asking. So we try to show things like the confidence interval, which is a function of the number of samples. We try to show the data ranges. We try to do other tests of the data to understand the statistical significance. And I think that most of these examples that we've been showing give you some sense of that. I know emissions characterization was of interest to the attendees of the earlier sessions that we've had, and so we have spent some time here talking about how you look at, try to understand emissions, and so some of the techniques we've talked about here, looking at chemical source profile comparisons, where you essentially compare an ambient fingerprint, if you will, of the pollutant concentrations with the emissions fingerprints that are available. And really, one of the things we want to remind you here is that you need to collect a wider range of pollutants than you think you might need to, because there's going to be other pollutants that may not be air toxics, for example, but that would be useful in helping identify the particular sources that you're looking at. And so we've really been trying to get people to think beyond just their air toxics, but also to this broader range of pollutants that are measurable by the same techniques, and that would be very useful. And by spending a little bit more money, you're going to get a lot more informative data from that. Another thing is we've shown you several plots where we looked at essentially the emissions activity, or the ambient concentrations, and comparing them to our conceptual model of how the changes in time of those emissions or those concentrations can be tied back essentially to the seasonal, day of week, or diurnal activities of particular emission sources, like mobile sources, for example, or that we might not expect any change other than meteorology if it's a 24/7 operation. And so that's something that we've shown you several examples of. Meteorological data is really important, and it's really going to help you figure out what direction the wind is coming from when you see the highest concentrations at your site. Can't downplay that enough. I mean, or that wind direction information is very important. And then source apportionment is another advanced technique that you can use then to try to look at emissions characterization. And there's quite a bit of helpful information on EPA's website on APTI, because or on the TTN, sorry, because it's going to guide you through some of the tools that are available out there for that. All right, we're wrapping up here in a couple minutes. Health effects assessment, we spent quite a bit of time today. Basically, you're going to try to look for your local, state, or national risk levels of concern, and those vary pretty widely across the nation. And really essentially what you're trying to do is pull together your data summaries and ensuring that you're using the proper treatment of data below detection, for example. And in all those cases, you're going to be working with your health risk assessment folks because we're data analysts and not risk assessment, but we have given you some resources in the last chapter of essentially of this information. There are some resources pointing you to some really good reading and helpful material. Other things that people have looked at is looking at baseline concentrations in the community, sometimes before some event's going to occur, like a new roadway or something. And in those cases, really what you're trying to do is pull together annual average information to look at trends. You need to understand seasonal variability in your data because it may be that you might have a seasonal pattern in whatever the new event is going to occur. And then you also are getting a starting line for what the air toxic concentrations are in your area before that event, and then you can figure out what you might need to be targeting as far as reducing emissions in the future. And then we talked about different ways to look at spatial variability. Always like to look at maps. That's a really great way to look at things. Methods evaluation, we haven't spent a lot of time talking about, but there's certainly some guidance on how to compare among methods. So we're ending up here with some more lessons learned from these data analysis projects that have been conducted by others and by us. And there's lots of lessons learned. And the first one here is plan for your data analysis in your study. And it sounds like a no-brainer, but often we spend so much time and effort and money collecting the data, validating it, that we tend to run out of time at the end. And so that becomes a problem. Really, it's really a big project management problem to come, have enough time at the end. And also having the right people in place to help you do the data analysis is important as well. The other thing we've said several times here is to make sure you're looking at your data really early in the project, because if it's not getting you the concentrations that you need to answer your questions, you need to readjust your plan. And that's really important. That's happened many times where the data is collected for quite a while, and at the end of the study, then you find out that it wasn't adequate, was bad quality, something happened, contamination, et cetera. So that's a big lesson learned from many folks out there. It's particularly hard to isolate an individual source impact on concentrations. Clearly, you need local meteorological data, and what I mean by that is probably co-located with your sampling location. But it's really going to be a function of emission strength, the frequency of the emissions that impact your site, the concentration levels, and it's going to be whether or not your conceptual model was correct or not, because you might have made the wrong assumptions. And then it's really also difficult to have data collected across many different labs, and so you need to do some extra quality assurance when you're using multiple laboratories. So that's another thing to remember and kind of build into your plan. And then the last slide for today is that you don't always get the answer that you expected. And so that's something to plan for as well, just thinking about, well, maybe it's not the pulp and paper mill that's got all the formaldehyde coming out of it. So that's kind of interesting. And I wrote some of the notes here is that, we start thinking about these projects. You want to have a conceptual model. Then you're looking for consensus across your analysis methods, whether to see if you're getting sort of the same answer across many different ways, and then digging in and doing a case study analysis of the unusual data. All those things will help you really better understand your data and give you more confidence in your results. I'll leave you with the fact that you want to look at your data, look at it often, look at it in different ways, dice it, slice it, map it, plot it, do whatever you can, and the more you look at the data, the more the story of the data comes out. And with that, I think we have just a couple more minutes if there's any other questions. We'd be happy, Mike and I would be happy to answer them, but other than that, we thank you for your patience for 2 hours of listening to us talk. I don't see any questions, but if there are, please let us know.
Next week.
Yeah.
Next week we're going from the beginning to the end with one project, starting from the very beginning of the project and why it was conceived, and then all the way to the end of data analysis, interpretation, recommendations, and what's been done. So it's a really nice case study, and gives a lot of interesting examples of what went right and what went wrong during the initial phases and the end phases and all along the way. So.
And I remember that you had to rush through it at the workshop, so it'll be really nice for you not have to rush through it this time. So I know that folks will really enjoy that.
So.
All right, I think we'll just hang it up now. Thank you, everybody, very much. And please tune in to Mike next week.